All right, so welcome to lecture 9, our first evening lecture, and we'll see how it goes. So far, I think a lot of people's liking this so far with this attendance, so that is promising. So yeah, let's do a quick recap. In fact, I'm going to talk through what we've done from lecture 5 to lecture 5, 6, 7, 8, 8, and then give you a few minutes to post a few questions on chat if you want to ask me to elaborate on them. I won't have this go past hopefully 7:20. My goal is to address any questions you want me to elaborate a little bit on. Okay, so we start from lecture 5, opening with asking the question, what is heat? And we provided the definition, and the definition is, well, we're motivated that it is not a fluid, which sounds a little bit almost misleading because we just lead ourselves in from the chapter of fluids. Nevertheless, we learned that although historically, because of the fact that heat seems to always flow from hot to cold, and it seems like that's where the term caloric fluid came from. It's a historical idea that is this mysterious fluid that flows from object to object, and that's why. And if you do some work, you can push the fluid back from cold to hot. But all of that is wrong. It is a transfer of energy. And what's the difference between that? Because if you visualize it as a fluid, then you would think that it is some sort of substance. But any substance cannot be destroyed out of or created out of nowhere. However, our great friend Jules, remember that little paddle experiment, a very simple experiment with a bottle of water, and then you drop a weight like this, and then now you have suddenly turned gravitational potential energy, that the weight is losing gravitational energy because it's losing height, as you can see, and it spins the paddle, and then now the temperature goes up, and then that's what we think of as heat. And you've essentially created heat out of nowhere. So it must be energy, because like since before Joules, Newton has taught us that energy cannot be created or destroyed, true, but it can transform in terms of its types, right? If you classify all the different types of energy, we talked about one classification very shortly, then energy can go from form to form. Now, physics does not tell you how do you do that. If you want to summarize what's the difference between physics and engineering in one sentence, this is it. Physics only tells you what can happen. Engineering makes it happen in that sense. Okay, so they utilize the theories inside physics to try to devise a machine, because when something can happen doesn't mean so in principle, there's nothing hard to go to space. According to physicists, you just need to overcome the force of gravity. There's no law in the universe to forbid you to overcome the force of gravity. If you have an upward force that is larger than a downward force, as we learn how to draw free body diagram, that is done. Now, engineering goes in to do the hard work. That is why I always think physics, we have the easy end of the spectrum, because the engineers, to their credit, it's a lot of very clever thinking in engineering a device in order to overcome that downwards force. The hard part is not to, so now you need to look at, okay, how do I actually maximize that force like that, right? So back to here is the types of energy it can transform from one form to another. It doesn't tell us how to do it, right? So although physics, of course, there's crossovers, it's not a clear-cut split. So there are applications we talk about, and in the end, when we lead on to heat engines, you'll see that how the principle of that can manifest into the transformation of energy as well. Now, there's a caveat in the heat over here, the definition, so do not end with just transfer of energy, actually transfer of internal energy. But don't just end here, it's due to temperature difference. Okay, so because normally if you just have the first part and you don't have the second part, now you might be tempted to think in equation form. Okay, that's in word form. In equation form, you might be tempted to think that, all right, heat is the transfer, so the change in internal energy. But you know that is not true. There's an extra term over there. And what is it? So let's, so we talked about energy can be classified into external energy and internal energy, right? So internal energy is any energy contained inside a system, I'm not too concerned about the rigorous definitions of these, to be honest. There's a few questions on Piazza. They're good questions. They're very good questions. In fact, sometimes there's some definitions we care more than the other. In this point, this is not one of them. So if you look, if in the exam, if you get this question, anything along the right philosophy is fine. In principle, external energy is just energy that's not contained in the system. But let's give a little bit more insight to that. Is energy due to some external sources, okay, or overall movement. These are the main two types of things that we classify as external energy. So energy due to external sources or overall, or energy of overall movement. Right? External sources, we talked about if you have an Earth over here and you have some objects, some mass above the Earth at some height, right? It doesn't have to be falling down, it can be put on a table, but the mere fact that it has some height has some energy, right? That is gravitational potential energy. Now, look, the physics does not tell you how do you transform that in a different type, how do you transform that to kinetic energy, right? It doesn't tell you that, but engineers can tell you that. All you have to do is push them off the cliff, right? Then you will transform it, right? This is very simple engineering. You just need a device that pushes it off the cliff, and you have magically easily transformed from gravitational potential energy to kinetic energy. Right? Let me not draw that. I just want to focus on the fact that this is gravitational potential energy. Now, this is due to external source, right? It's the Earth. The Earth is providing that energy here, right? The Earth is trying to pull it down. Or we gave another example for electric energy, electric potential energy. So if I have an electron over here, a proton over here, right, let's focus on the electron. The electron, just by the mere fact in the presence of the proton, it has this, the proton is trying to pull it together. And that's what we say, that electron has electric potential energy, okay? So this is actually what we'll cover in 2 lectures from now of what is electric potential energy, because you've learned gravitational potential energy. This is the next. Now you see external sources all usually comes from some sort of non-contact forces. Okay, so that's another way to put it. As long as you capture the essence of this, that is fine. Now there's one type of external energy, which is probably I should start with this, is overall movement, right? So any movement inside, like if the particles just are moving around inside a box, I don't care, right? If it doesn't contribute, if they all move in the same direction, now I do care. That is the external part. But if they all move in random direction, and for everyone that goes this way and hit the walls this way and try to move the box this way, right? If you hit the wall, though, it tries to move the box, there's another one that hits the wall the other way. So as a net effect, the resultant force is 0, that the box does not move. I don't care. That is not an external energy. That is all internal. But if there's more moving one way than the other way, if they're causing it to overall move in one way, you've got to understand that, for example, even if a car has external motion that it's moving one way, it doesn't mean every single particle is going forward, right? In fact, part of your wheel is going forward, the other part of your tire is going backwards. So it doesn't mean, if on a more microscopic level, the particles are, if you just zoom in and forget about a car, look at all the atoms, they're doing everything they're doing. But if there's a net motion forward, that is the kinetic energy that way. So these are a few examples if you need to give. I think these are the top 3 examples you can give as an example of external energy. Internal energy can be also kinetic and potential. We focus more on the kinetic ones because, as we mentioned, right, so they can be, right, translational, they can be rotational, and they can be vibrational, right? Zoom in a little bit. They can also have potential energy. Right. Now, what type of potential energy comes from some sort of non-contact forces? So I have these 3 particles again, there's some residue we talked about. There's a dipole moment and it's residual electric forces sort of pulling on, tugging on each other. So these are very complicated, right? So let's use our philosophy that if it's complicated, let's ignore it and leave it to the chemist. So physicists will deal with a simple case, and if we're talking about ideal gases, part of the definition is ideal gas has no potential energy, or all energy in ideal gas, all the internal energy inside an ideal gas is purely kinetic. Remember, that's one way of defining ideal gas. So let's, this is not in any particular order. I'm gonna just drop down things because the proper notes should be from before. Now I'm just sort of giving you the big picture and tying all the little loose strands together. Ideal gas, the main formal way to define it is gas that follows the ideal gas law, right? UV equals NKT, like that. If it follows that, that's good. But there's another 3 ways you can say, you can call it a property. I think I call it a property, but they're actually, it's actually, you can equally call it a definition. But let's call it a property because this seems like a more formal way of defining it. So one is it's only kinetic, all the energy, so some properties. It's only kinetic, no potential. Another word of saying is no intermolecular force. So let me fill this in as well, right? So the potential energy you can have is intermolecular energy, You might not hear this term said this way most of the time. You might hear force more, but it's the same thing in physics. Not the same thing, but if you're given a force, you can find its potential. If you're given a potential, you can find its force. They are basically related by this, right? So if you find a force, you can find a potential. This is a little bit out of what we're talking about, so let me go back to here. And even though chemists treat this as like a new type of force, a new type of energy, to physicists this is not. This is basically just electric potential energy that is leaking out. So you might have heard of the term residue electric potential energy that is leaking out of within an atom. Then it's leaking out, and now even though the proton and electron, true, it's neutral, but if they're shaped asymmetrically, now there's a net electric force in one direction or the other, and now that leakage is affecting other things. So since we are mainly, just for completeness, the third one is, what's the third one? No intermolecular force only, right, all collisions are elastic. Right. Okay, yeah, so technically any of these four versions you write down as a definition of ideal gas, it's technically all correct and all acceptable. Okay, so as you know, we turn our focus because you can imagine how complicated calculating residue electric forces are, that not only do you need a good understanding of the atom, you need to understand how it leaks out of the atom. So that is the subject of atomic physics or molecular physics, which actually starts to bleed into the area of physical chemistry as well. So this sort of goes into the more complicated side. So fortunate for you, you can shift your attention to just the simple side. If you know two formulas for ideal gas, you pretty much know everything about it that you need to do, right? And so if you simplify your state, because this is for gases, a lot of times you can approximate it as ideal. And speaking of approximation, you need to know when is it a good time to use ideal gas, and either it's very low pressure or very high temperature. I'm not going to re-justify that. You can look at your notes why we talked about these are the two good conditions. You can assume all the energy is purely kinetic. Incidentally, even at STP, standard temperature and pressure, right? Incidentally, even at 0 degrees, that's high enough temperature for gases to be considered rather ideal. Right, so that's internal energy, good. So, but there's one way to make it, so internal energy is basically just this. You can imagine we're focusing on this, we're not focusing on the potential part. Now, there's more than one way to increase the internal energy, because if you basically you increase it, you want to make the molecules go faster, right? Either jiggle faster or rotate faster or move faster. So you can heat it up for sure, but you can also try to squeeze them in. Now, if you squeeze them in, suddenly they hit on the wall more frequently, they collide more, and they have generally more motion, right? There's more collision per second at least, right? So, but however, this certainly will cause the internal energy to increase, but this is not due to temperature difference. So this is not called heat. We call this work done on the gas, right? So as you see, this gives us the first law that the total change in internal energy of a gas or of a system, right? System is more general now that we want to generalize, is the heat added to the gas, right? Heat added, let's say 2, we use the grammar 2, and the work done on the gas. Okay, so you can flip this around and see that this is the change in internal energy minus the work done on the gas, right? So you see heat is a transfer of internal energy, sure, that is for sure, definitely true, but you don't count anything that is sort of not due to temperature difference. So if you heat it up with a candle, with a Bunsen burner, and the gas moves quicker, that is heat, right? So heat is that amount of energy that comes from the candle. The other amount that comes from a hand pushing on it. Oh, that's creepy hand. Okay, not an artist, but if you push on it, now there is from an external. It's from an external source that increases the internal energies. It's some contact force in fact. So you see, these are non-contact force, and this is a contact force, right, to increase that. So we talked about, so this came from lecture, what was it? So lecture 5, we talked about the basics of that, right? So now that you add a heat to things, what will things happen? So you might be interested, okay, so if I have a box over here, I add some heat to it, what will it happen? Turns out solid and gas behave quite differently. for one, if you're able to keep this at a constant pressure for solids, usually the pressure is constant. Okay, you're kept at the atmospheric pressure whenever things are doing, right? So what will happen is you can use this formula. Right, I'll put a little p over here to tell you that it is constant pressure, but sometimes if it is understood, you can drop it. Okay? But remember, even if you drop it, that is the case you're doing. You have to use it for constant pressure only. So you see that if you add heat, it will cause the temperature to increase. Great. Now you also learned that whenever temperature increase, right? So you see that step one, the heat causes temperature increase. When temperature increase, it will also cause it to expand as long as P is fixed. Okay. So that is the study of lecture 6, right? And in fact, I grouped it into lecture 5, where we study this specifically capacity formula, but I relegated that to your own reading on that, which is mostly pretty straightforward. The subtleties in solving problems, the concept is pretty straightforward over there. And for gas, the pressure now can change. Right, so actually, all P, V, and T can change, and the correct formula for that is over here, lecture 7, where we talked about how you get the ideal gases. Okay, sorry, lecture 6. And then, sorry, these should be chapters, not lectures. Never mind, forget about that. You can look at the syllabus for the right numbering. And then this formula comes from the microscopic view, right? So the microscopic view, in fact, actually we found that the average kinetic energy of things, of an ideal gas, so if it only has kinetic energy, so we draw a box, we analyze the forces just from drawing the free body diagram, we realize that it is 3/2 kT. So each particle has 3/2 kT, right? So if you have n particles, then you have the total kinetic energy of the system, which is, if it's purely kinetic, that's also the total internal energy of the system, is 3/2 nkt. Okay. Right. So actually, we got 3/2 PV over N. So this is 3/2 PV, but PV equals nkt. So if you follow the derivation through, you actually get the second part, but in practice, this is more practical to use, that we tend to use. Okay, and then in the final lecture 8 is where we put it together with the first law and talk about all the processes, how you can change any heat added to it into the work done. Okay, so that is the big picture summarized in one slide. Any questions on this so far? Okay, all right, good. So that led us to the chapter of thermodynamics, right? So still continue on the recap on chapter 8. This time the number should be right. Thermodynamics, which is the study of turning heats into work or vice versa, right? And there is 4 ways of doing that. But why do we care about that? Is because we want to build heat engines. So to summarize that very quickly is to build heat engines, you need 2 criteria. You need it to be a cycle. So it's no good if you have a piston and you just push a box, right, from A to B, right? So the gas expands from A to B, then it pushes it from A to B. And it doesn't go back because that's a once-off thing. But now if there's a way you can cause it to be a whole cycle, so it goes back to the original state, and now you can have a continuous process and go on forever, as long as you have some heat that you can continuously supply. That's why for your car to work, you need gas, you need petrol, right? You need to go to the gas station and get fuel so that it can keep burning and make it expand. And then what it does, the internal combustion engine, what it does is it creates an explosion. So the gas expands and then the explosion ends immediately. So now it starts to cool down, right? It goes back down and then now it explodes again and it expands. So now you have this over and over again. So it's a lot of mini explosions going on, very controlled explosions going on inside, like little fireworks that keeps going, and that's gonna turn it on and run the engine, right? So you need it to be a cycle, but at the same time, this is important that we think about it less, is you need 2 reservoirs. You need a hot reservoir and a cold reservoir, right? So it's almost like water running down a hill where you have water flowing from hot to cold, and in the process you put your engine over here, and so we can symbolically, this is a very symbolic idea, that you put an engine in the middle that turns it into work. So there's the amount of heat going here, let's call it the amount that leaves the hot reservoir to the engine as QH, and the amount that goes from the engine to the cold reservoir is called QC, right? And you try to extract that flow out. It's like water flowing down a dam, flowing down a hill, you construct a dam, and you can extract the energy. Notice how physics doesn't tell you how you extract this work done over here. Physics just tell you can, right? So that's the engineer's job, to actually construct, put a nail and put a bolt over here and connect it in a clever way so that you can do that. So we look at a very high level idea on this side, and you can reverse that, just like water flowing down a hill, right? We tell you that if the water is on top of the hill, it has potential energy. Below, it has lower potential energy. If you can cause it to, so if it goes from high to low, it will lose energy, and it's your job as an engineer. We tell the engineer, it's your job to find a way to transform that into actually, electricity or whatever. And then they came up with the idea of building a dam, and then they come up with the idea of turbines and stuff like that. So if you're interested in that, you're interested in the engineering side of things. And we're here, whether you're interested in this or not, we are focusing on the high level, just the conceptual side of where does the energy go. And we can reverse that as well, and that becomes a heat pump, right? You can pump energy in here, and now you can actually cause the heat to go the other way around like that. So that's called a heat pump or a refrigerator, depends what you're interested in. So now it leads us to today's point of, all right, so that's good. What we want is, what is the best engine we can create? Because at the end of last lecture, we learned that it is highly inefficient, these things, because every time when we calculate the efficiency, which is another formula, right? Efficiency is useful work out of total input, right? So for the heat engine case, the useful work is that much, and the input that goes into the engine, so that this is the engine, right? The amount of heat that goes in is that much, right? So you see the work is the difference between the HQH and QC. And if you work it through, you find that, so this part from this step to this step is for heat engine. Okay. For a heat pump, the useful part might be different. You might be interested in how much heat goes out of your refrigerator, or how much heat that actually goes into your home if it's a radiator, right? So now you can simplify all this, and you can calculate, okay, so just to make things a little bit, just depending on the heat flow instead of what you get out of it. Yeah, so can we maximize this? What's the maximum of this? Right? So today we asked 2 opening questions. How to maximize the efficiency? Is there such thing as the perfect heat engine? And that I had a teaser at the end of last time. It's called the Carnot engine. And that's the theoretical best engine, the almost ideal engine that you can create. And how efficient is that? Today we'll find out. You can make a guess if that is if it's doing a good job or not, yeah, how close is it to what's perfect? What is the percentage? In fact, if you like, from your intuit, just from a pure guess, it's not an educated guess, but just any pure guess, put in a percentage in the chat. How many percent do you think? I'll write down the second question, and then I'll look at the chat and see if any one of you is close to a reasonable amount, somewhere between 0 and 100%. How efficient is it? All right. So as I write down the second question, I'll give you a few seconds there. The Carnot engine, at this point, if you're not interested in engineering, you might be like, who cares about this? Right? I'm more interested in the deeper questions in life. I want to know how the universe works. So this, surprisingly, it ends up, this chapter at the end of today, today's lecture will wrap up in a very beautiful idea called the Second Law of Thermodynamics, which shows us something very deep, a very deep insight about how the universe works. If I need to summarize that in one question, that is, why do some things happen and some things don't? If you think about it, it's very interesting. Now, some things don't happen because they violate, actually, a lot of things in physics don't happen because they violate a law, right? So if you say, can I create energy out of nowhere? No, it violates the law of conservation of energy. However, up till now, you will discover that there are a lot of daily life things that don't violate any fundamental law so far that you've learned so far, and yet they don't happen. For example, if you, let's go back to our Joule's example over here, right? The Joule's example, you drop the weight and then it turns the weight into heat. The paddle starts spinning and the water heat up. Now, is this possible to run backwards? Because if the heat drops down and then you wait for another day or two, suddenly the weight will start going back up, and then the water will turn the other way and it starts to cool down again. Does that happen? Now, that obviously you would start laughing because that will never happen. Now, what law does that violate? As far as you're concerned so far, as far as you learned, it doesn't violate anything. As long as the energy is conserved, if let's say the weight gains that much of energy and the water just cool down, so the water is just giving back in one way, you're transforming the potential energy into heat. Now, why don't you just transform the heat back into the potential energy and bring the weight up? Why does it not happen on its own? It can happen. You can try to grind it up, right? You can try to lift the weight up, but now you're inserting some external influence into it. But you understand, normally you just let go, you leave it be, it will go one way and it doesn't go the other. And in life, a lot of things happen in one way and not the other. Why is that? And to the end of today, we can address this question. Why do things don't run backward? It's a very interesting question. And if you drop an egg, it's another example of things. If you drop an egg on the floor, it splatters and it spreads everywhere, right? Why does it not go the other way? So you transform gravitational energy down here and then it splats. So you get some sound energy, you get some heat energy on the friction on the floor, spreads over everywhere. Now, if you take a movie of that, obviously, if you run it backwards and show people, you tell people this just happened in my kitchen, no one will believe you. But now you zoom in on every single molecule and you see that the molecule just starts moving in one direction and then they move, every single molecule satisfies the laws of Newton. If you zoom in and you forget about the fact that it was a broken egg or an egg breaking, just look at all the little molecules. There's no reason why it doesn't go the other way around. In fact, if you zoom that in and just look at each little molecule, just do its thing, and I show that film to someone else, they cannot tell whether this is filmed forward or backward or played forward or backwards. So on a microscopic world, it seems like everything is reversible, but on the macroscopic, it's not. And today we're going to learn why this is. Now let me take a look at the chat and look at the percentages. That is very interesting. All very good guesses, but guess what? That is completely far from not even close. You'll realize that actually heat engines are grossly ineffective. In normal operating conditions, we'll actually do a quick estimate. Oh, the last one is actually a little bit closer. Good job, Oscar. Wild guess, it's true, but yeah, normal operating conditions is around like 26% efficiency. That's the best you can do of any heat engine. We'll see how that works. Okay, with that motivation. Oh, it seems like these are two different questions, by the way. One is very practical, one is very abstract, or dare I say profound. But you will start to and then we'll realize actually the answer to the first one causes the answer to the second one. They're actually related. Yeah, right. Sorry, I should say one more. I should say the motivation for this is anytime when something don't happen, you want a law to tell you why it doesn't happen, right? So you make up a law. However, if you start thinking, okay, I want to say the law is you can never turn a way back up to change heat into paddles and into heating up the water. But then now when the egg breaks, you need a different law number 2, and say that this law forbids the egg. And then now you have, just to give you a few more examples. In fact, let's write this down. Examples of irreversibility. Right, so we have the falling weight turn into heat. This does not happen. A broken egg, broken glass, or anything, right? Go back to unbroken. It doesn't happen. A couple of other things. There are other things that doesn't happen. For example, you take a piece of block or brick or a wood, right, on a table. You push it, and then now it stops, right? So you push it and it stops. So the table gets warmed up a little bit due to friction, right? So the table's temperature increased just a little bit. Now you wait for a few days and suddenly the table cools down and then the brick starts moving again backwards. Now again, that doesn't happen, right? You can wait as long as you like. This motion will only go one direction. Or you take a bowling ball, you roll it. The friction is small, so it goes for a long time, but eventually it stops, and the whole ground heat up as it stops. You've transformed your kinetic energy into some heat energy that eventually all the kinetic energy is gone into dissipated into the heat. So why does the environment not just collect all that heat into the ball? They just all start just concentrating, like in a fantasy movie where all the energy just starts going into the ball and it starts moving again. It does not violate conservation of energy at all, but it does not happen, right? Another one is you take a box of gas and then you group it on one side, but now you suddenly remove the partition. And what will happen, right? So if you have perfume on one side of your room, and then you know this very well, you spray perfume on one side, and then suddenly it will start dissipate over to expand and fill the volume. But if you zoom in, if I take a movie of this and run it backwards, now if I look at the whole room, sure, everyone can tell it only goes one way and not the other way. But if I focus on each single particle, if you think about it, right? Each single particle, why does it not just, there's nothing wrong with them just going back into one corner of the room, but it doesn't happen, right? There's also one last thing is the phenomena that we motivated from the beginning of the chapter is the heat will flow from hot to cold. So when you put things in contact, right, they will become warm, right? So this again goes one way. If you take hot and cold together and it becomes warm, right? Now, if you cannot just wait for a long time. You can wait for a long time, it'll go this way. You cannot wait longer. So, or in any case, you just reverse your clock or whatever. It does not suddenly just go back into hot and cold, splitting it back up. So all these seems like very unrelated things. If you make up a law for one for each, you would have a very list that is a mile long. That is not an economical law. Turns out there's one law that rules all of this. So that's the mega law that we're going to find. And it's in terms of the idea of entropy. And this idea was discovered by Carnot and a few of his friends when he tried to find out the maximum efficiency of a Carnot engine. So this French guy pronounced Carnot, right? He realized, he came up with this idea of entropy, and he realized this is a very important quantity. And the one law that says is the entropy of the change in entropy of the universe has to be larger than zero. So entropy of the universe can only increase. And with this one law, you can explain all of these facts. Okay, so yeah, that is basically where we will get to. Okay, so we had so let's talk about that Carnot engine. So first, let's describe this engine, this supposedly ideal engine, right? So we'll draw the PV cycle over here. And how this engine is very simple. You take two isotherms. So you first start at some point with PA and VA, some pressure and volume. You do an isothermal expansion, go from here, and then you do an adiabatic one. And then you do an isothermal compression. And then you do an adiabatic compression. Okay, so it goes from A, B, C, D. Let me also draw its isotherms. So over here it's isothermal, right? Remember the isotherms is the curves of constant temperature, and they look like a 1/x graph. Of course, it's really NKT over V, right? So when you plot this, it's like 1/V, right? But the constant on top depends on the temperature. So the one on the top, the larger the value, it's the higher temperature, and the lower the value, the colder the temperature. So we have actually a hot isotherm, a cold isotherm. So you see from A to B, it moves along the isotherm like this. So let me put in the arrow as well. So this way, and this way. So when you draw these diagrams, make sure you put in direction as well. Label so the direction tells you whether it's a expansion or a compression. That adiabatic. And as we talked about last lecture, that so any ideal gas follows this. Also, if for adiabatic, an important formula is this, where this actually depends on the substance of the working substance inside your system, where that gas is an monatomic gas. I'm not going to write too much detail, or diatomic gas. Okay, so the adiabatic follows that rule, and yeah, an ideal gas. So in this process, it follows both. Yeah. So you see adiabatic is a steeper curve because of this, right? Instead of moving over here, you see if it's isotherm, it's PV equals to a constant, then it's isothermal. But here it's PV times something like 1.4 is a constant. So the volume changes much more, right? So in order to, if you decrease a certain amount of pressure, the volume would get would increase way more than the isotherm would. You can plug in some numbers over here, put in some test numbers, and you can see that it is the goal is that adiabatic is steeper. Okay, so if it's a expansion, it drops faster. If it's a compression, it rises faster than isothermal would. You see, if I start from D, if it's an isothermal compression, it will go along the isotherm, but adiabatic would go up, so it will increase, right? And it should also make sense if you ever want to think about this. So I remember adiabatic means you compress it very quickly, or it's very well isolated. So let's draw this. So it's very well isolated, or you do it very quickly, so there's no heat in and no heat out. So if you suddenly compress it very quickly, if you don't allow the heat to go out, where would it go? Well, it has to increase the temperature, right? So a compression, that's the only way you see it cannot stay constant. On the other hand, if you do it very, very slowly, then you're allowing heat to flow out, and you're allowing, yeah, I'll make it a little bit more porous, right? So if you compress it very slowly and then you have plenty of time for the heat to go out, you have a chance to maintain the temperature constant as you decrease the volume, like that. Not AB, but say initial and final. So you have a chance to create isothermal process if you do it slowly, but if you do it quickly, it will be adiabatic, like that. Okay. All right, so this is the Carnot engine. Okay, so let's ask two questions. Question one, what is this efficiency? That's our goal, right? What is its efficiency? Right? And question two is, can we beat it? Or why can't we beat it? Right? So this looks like a very stupid engine, right? or like it's nice and simple at the same in one hand, but why is this get so much credit? We'll find out. Right? So let's calculate the efficiency first. So I'm just going to quote what I got earlier, right? So for any heat engines, so this is true for any heat engine. Now you might think it might depend on the working substance over here. It depends on actually the working substance means the actual gas. It's called the working substance. Oops, sorry guys. Apparently the universe doesn't like me. Wait, does it say two of me here? Let's see what's going on. Okay, Zoom is Zoom is getting back to its senses. And pull the whiteboard back up. Sorry guys. All right, cool. Apparently Zoom doesn't want you to know why this is efficient. All right, can you hear me? Just checking, and let me just check if the recording is still going on. Yes, it is. Okay, good. All right, thank you. All right. I hope you don't lose too much. Good. So we're talking about efficiency over here, and this is the working substance. It's just the name we give to the gas that is inside this part. Okay. So so let's find. Can we just if I start at some hot temperature and some cold temperature, in these two questions, let me change the color. So if I start with let's say I operate between 100 degrees and 0 degrees, just making two random numbers over here. Can I express this just in terms of, if I just know what temperature it is it possible to find the efficiency? And the answer is yes. This is how we can do it. Remember the area inside here, that is enclosed inside the curve, when you have a closed curve, is the net work done of that cycle. Okay, so let me shape that in. So this is, because any area under the curve is work done by the gas, right? And any area under this curve is work done on the gas. So the net work done is the middle part. Okay, so I'll just shape the middle part. So this is the amount of work that is done by the engine. And I can actually combine. So I can say this is the amount of work done by the engine. Okay. And now over here, so wait, remember that diagram? Remember the heat flow diagram that we draw? Can we label the QH onto our diagram? QC and the W, can we label all these variables onto the diagram? So if we label this right over here, right, where's the heat go in? And the answer is it goes in here. Okay. So the heat goes in here. So this amount of delta QH flows in here, and the heat goes out in this process. So I've actually combined both my schematic heat engine diagram onto my PV diagram, right? So, okay, so you understand the shaded area is the work done, right? Why is the heat going in from process A to B, right? So let's ask ourselves, why not B to C? Because that's adiabatic, right? Adiabatic means no heat in and no heat out. So from B to C, there's no heat going in, right? From D to A, there's no heat going in or out, either way. Okay, so if there's any heat going in or out, it has to be either when the gas is performing the A to B part or the C to D part. Because when it's doing B to C, by definition, there is no heat in or out. Okay, now how do I know this is in? Because when you expand, what will the temperature do? When you expand, the temperature will usually drop if you don't do anything, right? So if you want to maintain it on the isotherm, you have to absorb the heat from somewhere, from the environment. So we can schematically draw this green arrow here to represent that the heat is flowing into the system. It is a very clever diagram to combine both of these pictures together. And then same logic over here. Now you're doing a compression. Now you want to do an isothermal compression. So if you compress it, normally when you compress it, you expect the temperature to increase. If you don't want to increase it, you better let some of the heat out. Okay, right? So you see why this is part where it's leaving the engine, leaving the system. So you can think of this as the system itself, the work done by the system, right? So you can have all these labeled over here. So what is the QH going in over here? Now, so the question is, what is QH and what is QC? Okay. Well, on an isotherm, the answer, let's see, yeah. So use a new page. So from A to B, it is isothermal, which means delta T is 0, the temperature doesn't change. That means delta E is 0 because E is 3/2 NKT as long as you're dealing with ideal gas, right? So if you put a change over here, you put a change over here, but N and K is the constant. So now you just have this, but if this is 0, then delta E would be 0. Okay. So for isothermal, delta E is 0. So from the first law, you see delta Q is negative of delta W, okay, on the gas, on the gas and on the gas. Okay. If you use by, then it'll be equal. Right? So if you use by work done by the gas, then it'll equal to the positive, right? But if you use on, it'll be equal to negative. So what is the work done on the gas from isothermal? So this is isothermal, which means, remember the definition like this. You first ask, is P constant, right, from A to B? Is P constant? P is not constant, so you cannot just pull it out. So you might be tempted to just use this, but that is if you can pull P out, right? So it's not constant. So you need to express it like this. Now T is constant, so you can pull T out, so you can pull everything out here, and you go through the logic, and I'll just write down the answer. I'll write dot 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 because we've done that before. Do the integral. Remember, integrate 1 over x dx is log, right? So 1 over v dv is log v. Log v, if I have AB over here, you need to plug this in. So this is the only calculus you need to know for this part. Sorry about my arrow. Yeah, so yeah, this is the only calculus you need to know about this to get this result. And yeah, so this is the work done on the gas. I'm just looking at the signs. So usually we don't care, we'll solve for, remember my advice is we solve for the magnitude and the sign separately. This is usually the best way to do it, okay? So what is the heat now, right? So ignoring the sign, it's just NKT log VB over VA. Okay. Now let me worry about the sign now. So the heat added to the gas is it positive or negative? Let's look over here. Heat added to the gas from A to B is positive, right? So the heat is going in to the gas because it's expanding. You want to maintain isothermal process, it has to be positive. So this is positive. Okay. All right. How about the amount that leaves the gas? Okay, so that is also isothermal. So it is exactly the same. So from A to B is this, from C to D also. So let's not worry about the sign too much. We'll worry about the magnitude first. Is NKT, so this is A, B, C, D. Log, it's also isothermal, so it's the same formula. I don't have to redo it. Oh, but you need to relabel it. This time is final over initial, like this. Now, this is very dangerous terrain when we see this. What is dangerous? Remember, whenever you have repeated variables, an alarm bell should go off and ask yourself, is this n the same as this n? Is this k the same as this k? The t is the same as this t, okay? Can you can you see which one is the same and which one is not? Right, nk should be the same, but t is not. The t, very good, well done. The t is, the first one is at the, you need to put either a or b, but which one should you put? It doesn't matter because a and b is the same, right? So let's just put th. And on the bottom, we'll put T cold, right? Because the temperature at A and B, look at the graph in your own notes a few slides up, right? It's the hot temperature, and then this is performed at a low temperature. All right, so what do we want? Remember, efficiency is we want to divide this over, we want this ratio. So this is actually, right? So the amount of heat that goes in, this is the amount of heat that comes out. So if we divide this ratio, we get, now, the question is, do I just get TH over TC? The answer is yes. Okay, so let me rewrite it in C over H instead. So we have C, H, and then we have this log VD, VC over log VB, VA. I'm flipping it around is because you don't have to write this little part. You have your notes on top of it. It's in a previous slide, so it's inconvenient for me. So I'll just copy it here. So I want this, so that's why I'm calculating this ratio here. Now, is this equals to 1? What is this equal to? Yeah, it turns out it's equals to 1, but why? So now we want to, so the question is VD over VC the same as VB over VA, right? You see, if this is the same as this, then the whole log divided by the whole log will be 1. Okay, so it turns out this is true, but why this is true? We've used the fact of isothermal so far, right? So notice we've used the fact that A to B is isothermal. We used the fact that C to D is isothermal, but we haven't used the fact that B to C is adiabatic and D to A, D all the way back to A is adiabatic. So let's use that fact and see if we can learn anything new, right? So the adiabatic part, let's look at from B to C. Remember, look at your own diagram. I'm not gonna flip back and forth. So we have adiabatic means we have this satisfied, right? Can we utilize this? First of all, I want to link T with V, not P with V. So let's rewrite this in a slightly different way. Because it's always an ideal gas, I'm always free to use the ideal gas law, right? So I'm going to replace P with NKT over V so that I can connect T to V, okay? Now I have T times V gamma minus 1 equals to another constant. I'll put it as constant prime because N and K is constant. So if I divide to the other side, we have this. Now, I don't really care about this gamma minus 1 factor. It's just a number, whatever, 5 over 3 minus 1. It's another decimal place, another fraction. It's not a big deal. The big deal is TV to some number is a constant. Okay, so let's use this, right? TV to some number is a constant, which means you can compare 2 points. What points do we want to compare? Well, let's compare from B to C is adiabatic, right? So let's compare that. So from B to C, let's compare these 2 points. So this should satisfy this, right? So this number here is gamma minus 1, but I don't care. It's just some number, okay? Now, all right, I can say the same thing for from D to A. So this is from B to C. When D go all the way back to A, I can make the exact same argument, right? So I can say A and D is related this way. Okay. And now I'm repeating variables, right? I'm repeating this number. Is this hashtag the same as this hashtag? Yes, because it's gamma, like just going from right B to C and D to A, it's the same gamma, it's not different. All right, now what do we want? We want B over A, B over A. Okay, let's divide this on both sides. Okay, let's zoom in over here. What can we learn when we divide this? All right, we want B over A. How about TB over TA? Can we say anything about that? Now, coincidentally, this is equal because it's an isotherm. Remember, we just talked about over here that A and B shares an isotherm on the TH. So these are actually TH, and this, look at your own diagram, this is T cold. So we conclude that VB over VA with some number raised to some power is VC over VD raised to some power. Did I get my direction right? Let's see. So you see VB over VA. This should be flipped. Where is that? Oh, I said I would take out the sign and then I forgot. This is the danger of that. Right, so QC is this amount leaving the system. Okay. So there should be a minus there. And a minus would flip this around. I apologize for that. Right, so it will flip this around. So at the end, we write this is VC over VD. Okay. So our question should be, this. And as you can tell, yes, you can just raise it to the opposite power. And you see VB over VA is actually equal to VC over VD. Okay, so we learned that this is the conclusion. Right? Okay, so what this looks, so this is the ratio, which means you might want to put a box around this because if you ever need this, we'll give you this, or in your cheat sheet, you will just write this down, and if you need to use, just use it. Some derivations you want to know, some derivations you just want to see it once in your life. This belongs to the latter. You want to see it once in your life to know that it can be derived, and it's not some magic thing that I pulled out of my hat. It does come from just looking at whether things are isothermal or adiabatic. You piece things together in a very clever way and you get the result. So you don't have to reproduce this, so don't worry about that. Let's go back and try to understand what is the physics out of this, right? So we got TC over TH. Good. All right, so let's plug in some numbers. Let's assume we operate this engine. Let's go back to that percentage that we were throwing out. So the efficiency of Carnot is 1 minus TC over TH. So let's plug in, should we plug in Celsius or Kelvin? Good job, should be Kelvin, because any physics formulas, when we derive it, we don't care about Celsius. We use the fundamental, the ideal gas law. Remember when we draw the graph, it doesn't follow linear proportionality if you use Celsius. It only works, the ideal gas law only works if you extrapolate it to Kelvin. You start your plot from Kelvin, right? So make sure any physics formulas is derived from Kelvin. Before you plug in any T's, if you're not sure whether you use which, Kelvin will always be right, okay? So you plug in, the cold temperature is 273. Let's put it at some, let's say the melting point, right, of ice, and some boiling point of water. Okay, so you go and plug in 273, divide by 373. You get this, minus 1 is, should be 1 minus, I'm just doing this quickly, 26%, 26.8, let's say 27%. Okay, so if you operate your engine at 100 degrees and 0 degrees, right, then the maximum efficiency of useful work out of the total input is around 27%. Now, in real life, in our car, in our internal combustion engine, the cold reservoir is the environment, which is more like 20 degrees. So if we want to maximize efficiency, what do we want to do? We want to make this as small as possible, right? So you basically want to make TC as small as possible and TH as large as possible. In other words, you want to make the gap between hot and cold as large as possible. So you want TC as small as possible and TH as large as possible. Okay. So in real life, probably we're at 20 degrees outside. Today it's probably more like 40 degrees in California, but something like that, right? But the TH is also very high. I have actually no idea in the gas tank. It's pretty high. So it's not always 27%, but it depends on this it has a limit, and the limit can be calculated by this. Okay. All right, so good. So if you're an engineer, you'll be very happy with knowing you have a limit, and then now you know the strategy of how to maximize this. If you're an environmentalist, you might be a bit bummed about about it's not as high as you think. You can try to think about, okay, let's say I want to, and actually this is a nice exercise for you. If you need this to be there, you can't change this. What do you need for this if you want 50% efficiency, right? So let's flip this around and ask, what does TH has to be for 50% efficiency if I cannot change the TC, if the TC has to be, if my exhaust pipe has to go out to the environment, right? All right. So this is you can give it a check. I have no idea. Plugging the numbers it's very simple, and then you can find out and probably tell me on Piazza or something. Okay. So yeah, but now if you're an engineer, you're happy. If you're an environmentalist, you might not be. But what if you're a physicist? Right? What can you learn from this? You want to see if you can beat this, if there's a theoretical way to beat this. And Carnot have this argument, and it's called the Cardinal Theorem. It's a great argument. It's a diagram. He drew a diagram and was able to argue that basically. I'm not going to write too much things. Let me just give you the main ideas. I think that's more efficient for me. You can read on the book on the relevant chapters, and I forgot the relevant chapters. Look at the syllabus. Right, what did he say? Cardinal Theorem say, basically, no one can beat me. This is the best you can do, right? So why is this? So let's do something fancy called proof by contradiction. Let's imagine you can beat him, right? So let's see what goes wrong. Does the world break apart if we beat him? And it actually does, right? So first of all, Carnot needs assumption. He assumed that heat can only flow from hot to cold spontaneously. So this is his starting point, Carnot's assumption. Okay, we're not trying to prove this point. We're going to use this fact that it only goes from hot to cold spontaneously to show that the Carnot engine is the best in the industry. Okay, now it doesn't mean that heat can never go this way, but it cannot go this way spontaneously. That is very important. Okay, because if you put in some work, sure, that is basically the idea of heat pump, right? You can pump them up. But I'm saying if you don't put in any work, it can only go one way. Okay. All right. So now he start with this assumption. All right. So now let's assume we have a better engine. So this is your engine. Okay. Whereas this is Carnot's engine. Okay. So Carnot engine is going to draw in, let's say, 100 joules of heat. It's gonna do, let's say, 20 joules of work, right, around 20%, and then it expels out 80 joules of heat. Not very efficient, as we saw, but this is the way it is. Okay, let's say you come up with a startup company, and right, you go to Tesla and say, hey, I came with a nice idea where it will produce 40 joules of heat. Let's see if you can fool the leaders that be in Tesla and believe you or not, if this is possible. Right? We're operating on the same temperature, same hot and cold temperature, because sure, if you drag it larger, we know you can maximize the efficiency, but in the same temperature, can you make something more efficient? Is this possible? Right? So your venture investors will look at this, and this is what they'll think. Right? So first, let's reverse the Carnot engine. So you can reverse all the direction of everything, right? You can put in 20 joules and you can reverse everything. You're just running the Carnot engine backwards. It doesn't, that doesn't violate any law. You can do that, all right? And now you take two of them and connect it to your engine, right? So I'll take two Carnot engines. We take the bottom Carnot engine. We take two of them, right? We take two of them. So this time, if I take two of them, I'm going to need 40 joules of heat, right? 40 joules of work, sorry. To do 40 joules of work, and then I can I can draw out 160 joules from here and then 200 joules over here. Okay. First of all, this doesn't make it more efficient. You understand? It doesn't take a genius to put two of the machines together. Because you just need more work. It's not more efficient. Okay. But now, as soon as you connect this with your engine, that takes 100 joules. And produce 40 joules of work and expels only 60 joules, like this. And you take your engine and any work that comes out of it, you use to drive the two Carnot engine and pull it up. What happens? So you take this. So what happens is, let's just look at the bottom over here. You will see that there is, in total, how much heat is going on top, how much heat is, how much heat goes into the hot reservoir, into TH? Well, there is plus 100, minus 100, right? So there's 200 going in, 100 going down, okay? So this is your engine, you pull your imaginary great engine, right? That takes 100 joules, it does that much of work. You couple that work into the Carnot engine that Carnot developed 300 years ago, 200 years ago, and then you take two of them, right? And then you drive it up. So now there is 200 joules going up, 100 joules coming down, right? How much heat is leaving the cold reservoir, right? So yeah, so you see there's a total of 200 joules going into TH. How much is going out of TC? Okay, so there is, or let's say how many joules goes into TC, right? So there is 60 joules going into it, but there's 80 and 80 leaving it, right? So there is overall 80, 80, 160 plus 60 minus 100. Sorry, that was a typo. 100. Good. Right, so there's minus 100 joules going into TC. So there should be, so leaving TC is 100. And into TH is 100, right? That makes sense, okay? So what we conclude is going out over here, there is 100 joules going out of TC, and there's 100 joules going in to TH. What's happening in between? Now if you zoom out, you don't care, you put a black box around this, because you notice now, if you put these two together, you no longer need to plug this into any external outlet. You don't need to plug this into the wall, right? Because here, this engine just not automatically, let's say outside is very hot, now in California, outside is very hot, inside is relatively cooler, right? So between your walls, you install your engine. Right next to your wall, right? Just right next to it, you install two Carnots, or a Carnot that is twice as big, right? So you have the outside temperature, you have the inside temperature, and suddenly you don't need to plug this into any electrical outlet anymore, right? Now it's from your engine, it's going to produce the work to drive the other one that extracts the energy from cold to hot. Now you have a free air condition that is drawing all the heat from inside your cool little house, right? Right? So you can connect your hot reservoir and your cold reservoir like this. And you have overall, just every day, just drawing free energy from cold to hot outside. And that violates his initial assumption. So as a result, this is the argument. Hopefully you understand this. Again, you're not required to reproduce this. You might be in the exam if you're worried about exam, which is not going to be tested in tomorrow's test. You might be in a test or an exam, maybe you'll get these sort of questions, which is calculate the efficiency of a certain Carnot engine. If I give you the outside is 100 degrees, inside is 20 degrees or something like that, you might be getting this. You won't be able to, you won't be asked to reproduce these arguments. However, hopefully you can appreciate this, that this is the reason why this is complete nonsense, that you cannot create an engine like this. Otherwise you will violate this. All right. Apologies for the time. I still will probably go over a little bit today. I'll keep it in the recording. If you have something to do, as usual, you can get on with your life, but I'll have this rest of it recorded. All right, so good. So now we finished the engineering part. Let's go to the second question of today, is the second, why do things don't run backwards? So this is probably one of the most profound laws in physics. It's called the second law of thermodynamics. And this is basically the mega law that tells you what is allowed and what is not allowed. It comes in three flavors, okay? So there's the first version, which actually, so it's called the Kelvin-Planck version, right? Kelvin and Planck came up with this and basically say that what I said already. So this is not possible. It says that heat cannot spontaneously, you can read the textbook for the correct wording, I'll just save time and just write out a keyword. It cannot spontaneously go from cold to hot. Okay. So that's one way of stating the second law. The second way is Clausius' version of saying it, but I'm going to hold off of that a little bit and give you the third way. It's the entropy version in terms of entropy. So you introduce a new concept called entropy, and you say for everything that happens, this S, this entropy is called S, will change. And the law tells you that, and you add every entropy in the universe, it has to increase. So why is there 3 versions? It's because although they came from 3 different parts of history that different people came up with them, they thought it's different statements, but then in the end, a genius guy, probably Boltzmann or some of his friends, figured out that all 3 are the same. If you start with this, you can prove this. If you start with, and then you can prove this, or you can start with this and prove this, or you can go this and this. So they're all basically the same way of saying the same thing, okay? So instead, you notice in Carnot Engine, I started with this and proved that the Carnot Engine is the best. I can now actually start with something more technical and less qualitative this way, right? Because with this is good for heat engines, but it's not good for me unbreaking an egg, right? Or making the bowling ball go backwards and the floor cool down and then the bowling ball reverse its direction. That's not very useful if I look at it this way. So we want a universal and quantitative way to calculate it. Now, incidentally, there's Clausius' way, which is actually written like this, which is basically saying this is not possible. You cannot turn all your heat into work. So 100% heat engine, efficient heat engine is not possible. Okay? And as you can probably tell with basically proof that if you assume this is automatically true. Although this is kind of obvious how it comes from the first version, its implication is quite profound in the sense that there's no way. Now I challenge you after today's lecture, you go out and look at any machine that has to do with heat, including your refrigerator, including your car, including the bus on the street, including a power plant. Everything has an exhaust. Everything you need the heat to be exhausted somewhere else, right? Whether it's your car, your refrigerator, your AC, look at your AC at home right now, right? It has an exhaust pipe, even if sometimes it's hidden in the wall. Or if you have a primitive version like I do, then you actually have to connect that exhaust pipe, right? So this is, the implications is important over there. All right, what is this entropy over here? Now, you need to understand there is 2 concepts. There's absolute entropy and a change in entropy. Turns out, with what we learn in this course, there's no way for you to calculate absolute entropy. So what is delta S? Clearly final minus initial, that's fine. But what's interesting is in this course, you will not be able to calculate SF and SI individually. You will be able to calculate delta S directly, okay? And we'll give you a definition for this, and we'll not give you a definition for this. The idea of absolute entropy actually came later in the history of physics as well. People were able to calculate the change, but not the definition. So that is a little bit more advanced and it's out of the scope of this course. But for us, we actually don't need it. It's actually much simpler to just look at the change. So let me give you the definition, not of entropy, but the definition of change in entropy, okay? So in symbols, it's defined for every process you do, it's the amount of heat, the entropy of a system, amount of heat into the system, right? So into, remember, make sure you not out of, but into the system, divide by the temperature of that process. Okay. Okay, so this is the definition of change in entropy. Okay. So first thing you learn over here is if the heat into is positive, then the change in entropy is positive. Okay, so if you have an engine, you go here, or let's draw a PV diagram. Let's draw that Carnot engine. In this cycle from A to B, the entropy increases because heat is flowing into your system. But in the other part over here, heat is going out, right? So the heat into the system is negative, which means heat is going out, then your entropy would decrease, okay? But the second law say that when you add up, right, this process plus this process, when you add them up, so S total has to be either 0 or positive. This is what second law claims, okay? Now, if it is positive or 0, if it's positive, it is allowed, okay? So if you drop an egg and it breaks, you calculate the entropy change of the egg and the environment, it should be positive, so that's allowed. If it's 0, not only is it allowed, it's also reversible. you can go the other way because it's 0. That means if you go one way, it's 0. The other way is also 0. So that's fine. But if it's purely positive and then you go the other way, then it's not allowed. Because if you do it one way and then you reverse it, then you reverse your whole process, then these two signs will flip, and overall you get a negative in the universe, then it's not allowed. So the egg breaking, unbreaking will actually, if you do the math, it will tell you it is not allowed, okay? So let's see, let's do an example and you'll see how this works. And I will use the example of hot and cold mixing, okay? So as we know, when you take hot and cold, let's take two equal mass for simplicity. So this is at a hot temperature, at a cold temperature, you put them in contact, right? And now they will arrive at a final temperature, right? So technically, you need to do the whole heat gain equals heat loss deal, but this is, I made it simple so that they're equal mass. So this is just the average of them, right? So just hot plus cold divided by 2, right? It will just be the average temperature when you put two things of equal mass together. I think that's obvious. So let's find out, right? We'll calculate the entropy in this direction, and then we'll reverse it, okay? So let's do some quick exercises first. What happens if the process is adiabatic? Okay. What is the entropy change of adiabatic? If it's adiabatic, then let's put in this, right? This should be very simple. Can you tell what is the change of entropy for an adiabatic process? It should be 0, right? Because adiabatic by definition means no heat in and no heat out, right? Whatever temperature you're operating on that process, it doesn't care, okay? Good. How about if it's isothermal? Now this is more tricky because when you look at this is not a constant. Sorry, this is a constant, right? So it is simple. This is constant. So isothermal, so this is constant, all right? So we just need to use the formula for isothermal, which we have shown, right? Log VB over VA over the T, which is, now I don't really need to worry about that because the T is constant in this process, right? So that cancels out, which gives NK log VB over VA, okay? Now the next example is not constant, right? Let's talk about isobaric. Now, in an isobaric graph, how does it look? Well, the graph is simple. It looks like this. The pressure is same. It goes from VA to VB like this, okay? This is the work done over here. The work done is P delta V, right? It's very simple. But now, the T is not constant, which means, you see why it's not constant, right? Because it's going from, these are the isotherms. And you see as you keep going this way, it's moving from low isotherm to high isotherm. So it's going hotter and hotter, right? That way, if you expand it that way, okay? The reason is because normally if you expand a gas, the pressure would decrease. If you insist on the pressure not decreasing, you better increase the temperature as you go, every step you move. Does that make sense? So that's the only way you can create an isobaric process, right? So the temperature increases makes sense over here. So you can't directly use this, but we have a clever way to do this, is you look at the infinitesimal idea, okay? So this, if this is equals to this, if delta S is equals to delta Q, then the small change in entropy must be a small change in heat. Okay, so read this as a big, or sometimes called a finite change, and read this as a small change. I know it looks like calculus, but don't worry about that. Sometimes students immediately get scared. Here I'm telling you, don't be afraid of this. D is just a small change, okay? All right, so lesson number 1, learn that D, whenever I write D, it's just a small change. Lesson number 2 is learn this relationship. Now, how do I read this? Read this like a big change is equal to adding up all the small changes. So lesson number 2, learn what does an integral mean. An integral just means adding things up. I know there's a lot of mathematical formula like big change of what? Finite change, because sometimes we call this as infinitesimal. So infinitesimal and finite, infinitesimal. slash small change. I try to not use like scary jargons and just use big and small, right? It's easier to think of it that way. So yeah, you've learned a lot of rules, substitution, power rule, whatever of integrals, but it's at the end of the day, an integral is adding up small changes. It will give you a big change. And I think it's always good to label this. Now you understand, on a side note, why my insistence of you writing out a delta Q, because we're going to use this very shortly. And to me, it doesn't make sense if you do this if you don't write the delta for Q and you write the delta for S. S is non-negotiable. You have to have the delta because, as we said, absolute S and change in S is two different things. We are learning about change in S, right? Q, the justification of dropping the delta is because without the delta, just Q does not make any sense. There's no such thing as, because Q fundamentally is a transfer of heat. So you have to have a delta. So people go lazy and drop that. But now the equation seems very asymmetrical because I'm going to use this a lot, right? If you're comfortable with this, that is fine. Working physicists are actually very comfortable with this. But to me, this is always a nice way because you actually read it as big change. This is my primary reason, although I've given several reasons before why I like having that. This is my primary reason of why I like that. Okay. So let's go back to my question of isobaric, right? Isobaric, first you need to understand why just calculating this does not work because T is not constant. If you look at the isobaric. So you need to do this from initial to final, let's say from A to B. Say initial to final, just be a little bit more general. All right, so I will use a small change. I'll use this fact over here and write that here. So far from this step to this step, it's just definition of ds, of the change in S. Now, because it's isobaric, so that means pressure is constant, right? If pressure is constant, I can use this law, right? But this is for a big change. Let's do it for a small change. Look how easy calculus is. This is just big change, this is small change. Now let's plug that in here because this is isobaric. I'm perfectly allowed to, just to emphasize, right? Isobaric, I'm perfectly allowed to plug that in. And pull out the constants. This is a log. Now you can do the math. It's going to end up as log TF over TI. So this is for isobaric. Isothermal is NK log VB over VA, or V final over V initial. Adiabatic is 0, just for reference. Volumetric, I'm not going to do it now. It's not too important to our discussion. These three are more important. Okay. So what was our question? Let's not veer too far, right? Our question was trying to connect the hot and cold and calculate the entropy. Now, this is exactly a calorimetry problem where we are operating this at constant pressure, right? So you know how to calculate delta Q, right? So now let's calculate the delta S of this process where you go from initial to final, right? You go from hot to final, this goes from cold to final, okay? So for the hot object, what is the delta S of the hot object? Well, it's MC log TF. So TF is the hot over T final, right? Sorry, final minus initial, final over initial, final over initial. And delta S of the cold object is MC log TF over T cold. For the hot object, it's going from this to this. The cold object is going from this to this. Now, how about the sign? Which one's positive, which one's negative? Remember, when you gain heat, this is roughly the idea, right? If you gain heat, you gain entropy. If you lose heat, you lose entropy. So the hot object loses heat, so you should lose entropy. The cold object gains heat in the process, you gain entropy. All right, so one loses and gains. Let's add them up and see if it's larger than 0 or not. So let's see if it's allowed or not. Okay, so we add this up very easily. So S, and we assume this is completely isolated. So there's no more, there's no entropy. The whole universe consists of just this. It's perfectly a closed system, right? Yeah, there's no external influence. So the whole universe, or just the total, is S hot plus S cold. I'm going to read S hot and has cold. I'm not reading delta S, but understand there's a delta. It's just for ease of communication. All right, so there's MCP and log of minus log of TF over TC plus log of TF over TC. Oh, sorry. I don't need to explicitly put in the minus and plus because let me just look at this. TF is smaller than TH, right? So log of a number that is less than 1 is automatically negative. So if I put an extra negative here, I will be double counting it. I don't want to do that. So I just need to make sure this is less than 0 and this is larger than 0. And that is true because this is less than 1 and this is larger than 1. Another thing you'll need to learn for this course is you need to learn how does a log graph looks like. So if any x value that is larger than 1, the log is positive. Any x value that's less than 1, right, log x is negative. Okay, so this is the right direction automatically. I don't need to artificially put an extra minus sign. That's a mistake because if I artificially put it, now I will have negated it, right? I'll make it overall positive. Okay, so that should not be there. Okay, now let's combine the logs. TF squared over THTC, like that. Okay. Now, is this larger or equal to 0? That means we need to check if TF squared over TC is larger or equals to 1, right? We want to check this. Let's just keep it simple. Is this larger than 1? Yeah, let's make it larger equal to 1, right? That so that's equivalent to saying is TF squared larger or equals to TH times TC. Okay. Now, what is TF squared? For our simple example, it's just the average of the cold, right? It's this. So TF squared is TH plus TC over 2 all squared, which is TH squared plus TC squared plus 2THTC. Let's just expand that over 4, right? So now you have TH squared plus TC squared over 4 plus 1/2 THTC. So is this larger than just THTC? So you can plug that in here and check that. Just for time purpose, I will tell you the answer is yes. It's around 4 more lines of moving things from left to right and right to left. Nothing profound, but ultimately you will find this is yes. Okay, so you'll actually find that TF minus TH minus TC or something like that is larger than 0, which is true, okay? Because any squares has to be larger than 0. I'll probably put in the extra slide of notes later. Okay, so it does happen. So you see that from hot to cold, it does happen and it moves down, where was my object? Yeah, here. So it goes from hot to cold and they equilibrize. Yes, that does happen. Now, if I reverse every single step and you understand that then all the entropy will flip because now originally my hot object is losing heat, the cold object is gaining heat. But now if I go the other way around, if I try to make it go the other way around, then I need to flip every sign and then my entropy of the whole system would decrease if I go the other way around, okay? And you see that this law will forbid that from happening, okay? Now, obviously calculating this for an egg is much more difficult, but so we're not going to do that, calculating for a bowling ball, but the takeaway from here, I think, yeah, I'll be able to end the lecture just to give you guys, all of you very dedicated students who are staying, just to give you an idea within 5 minutes, no more than 10 minutes. Okay, so within hopefully around 5-ish minutes, I'll be wrapping this up. The bottom left says TH minus TC. If I've done my math correctly, this will lead to, if you plug this in here, step 1, plug it in, and then move things around, try to achieve this goal. Actually, it's a nice exercise. Anyone have trouble with that? I'll probably include an extra slide and just send it to you on Canvas to save time. So let's talk about the physics and the implication of this. Right? The math we're done for today. Right? I just want to comment on this is right. So we talked about the egg. Of course you need to calculate the entropy of every little bit of particle breaking. That is more complicated. So when you have simple systems like this, if I have unlimited time, I can actually do this process for you of this paddle, right, to show you why it goes one way, and that after it goes down and the temperature goes up, the water will not spontaneously cool down, and then the weight just magically go up, and then transfer the GPE into so take the heat energy or internal energy and translate it into GPE. It doesn't spontaneously do that. It is from calculating the entropy change of this process and add them together. Now remember, entropy itself can decrease, so this is allowed. But when you add up everything, total entropy of a closed system, so sometimes in physics we just call it the entropy of the universe. It could be a small universe as long as it's closed. Then it can only be positive. Okay. So individual process it's allowed. In fact, just a reminder, right? This is the definition of delta S. So if you lose heat, you decrease. Very simple. Gain heat, you increase. But if you gain heat and if you gain heat, if you lose heat, where do you lose the heat to? If you lose the heat, it will lose to some other things, right? So because heat is a transfer, it will go to the environment. And actually, here's another example. If I have a block of ice, okay, and if you put it in normal day, right, it will melt. So what's happening over here? The heat is going out, right? In fact, it's ML fusion, vaporization fusion, right? So it's MLF. So in fact, let me make this a little bit more symmetrical, right? That amount of mass will get changed. So the heat will go into here, okay? So what is the delta S of the ice? The delta S of the ice it should be a positive value because it's gaining heat, right? So it's gaining heat to melt at T. So this is mass of the ice times latent heat of fusion of the ice. And the temperature is 0 degrees, which is 273, right? All right. And how about the environment? Well, the environment will probably lose heat. So this is the heat to the ice. So what is the change in heat from the environment to the environment? Well, from conservation, so this is T of the ice, T of the environment. But from conservation of energy, we know that heat loss equals heat gain, right? So the heat gain by the ice must equals to negative of the heat loss of the environment. This is from first law, or conservation of energy, or whatever you like to call it. Maybe not first law directly, but just conservation of energy. So this is equals to negative of the heat to the ice, T environment. So this is negative of M ice, LF ice, over, what's the environment? The environment is maybe 20 degrees Celsius, so 293 Kelvin. Which one is larger when you add these up? Well, the top is the same, right? When you add it up, which one is larger? The bottom, one of them is larger than the other. So the environment is smaller, right? Because you divide by a larger number. So this is a smaller amount. So you decrease by a smaller amount and you increase by a larger amount. The ice is gaining heat, so it's positive. That's good. Let me just check the sign. This is M is positive, LF is positive, this is positive, but heat gain equals negative heat loss, right? Or if you put it the other way, heat gain plus heat loss equals 0. Right? Either way you want to do conservation of energy. And yeah, so this sign makes sense. This is overall negative. So you add these up and then you see that this will overall be positive. Okay, so this is allowed. And if you flip it the other way around, it's not allowed. Right, so now you realize why the ice will melt in normal condition and not the other way around. If you put some water over here, it will never spontaneously go backwards, right? So you see entropy is very powerful. This is another nice illustration over there. Sorry, I lied. I say I won't do another calculation, but I just did. Hopefully you enjoyed that as well. And the final thing I want to tell you, I'll just say it more in words than write it down. You can read it at the end of chapter 20. I forgot the sub-chapters. I'll put it in. Right. It's at the end. It's called the heat death of the universe. Okay. This actually, so what we learned today will actually have some pretty big implication. And in the long term, it is actually pretty scary if you think about it, because what did we learn about heat engines? Heat engines means you need two reservoirs. Remember, I made a big deal with it earlier in the lecture today. You need two reservoirs. You need a hot and cold in order for you to do any useful work out of this. Now, we just learned now at the end of today's lecture that whenever you have hot and cold, there's only a chance that they will go and neutralize, but never a chance that automatically, without doing work, they will split up. That means this process is irreversible. At some point in the future, in the far, 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 far future in our universe, everything will eventually go to the same temperature, right? So because we keep doing work every day, right? We have lots of machines that is taking heat to flow in this direction. If you want it to flow the other direction, you need to inject heat to make it go up, right? To go the other way. Now, where does, let's say you want it to go the other way because ultimately you want it to go down. So where does this work come from? This work must come from some other source, right? So you first need a hot and cold. Can you see the problem now? Eventually, there's a chance when things will get to equilibrium, but never a chance that automatically they will separate. That means at some point, there will no longer be a hot and cold reservoir. The whole universe would go in some equilibrium temperature. Imagine when that happens, how can you separate out the temperature again? There's no way to do that. That is the ultimate death of the universe, where everything becomes a thermal equilibrium. Because if you want to make a small pocket of the universe, I want this part to be hotter, this part to be colder. I first have to do work to separate it out. But where does that work come from if I do not originally have a hot and cold reservoir? So this is not something you have to worry about the future, not in the near future at least, but it's something that physicists sometimes lose sleep about and think about. So I'll just sort of end in this positive note for today. It used to be, whenever in the past, whenever my professor teach this subject, they used to make a joke that although this sounds very grim, that in the future, first of all, it's not happening anytime soon, and anytime in the near future, we probably have to worry about either a nuclear bomb or a pandemic before we need to worry about this. But that joke doesn't really age well nowadays anymore. So in that case, you understand how entropy works, and that wraps up the whole topic of thermal physics. Right. So I hope you enjoyed this. Sorry for the slight overrun again, and we'll begin electricity and electric forces in the next lecture. Okay. All right, good. And have a good night, everyone, and good luck for tomorrow.